computer. And now, okay, this should record, and I will record the video. I'll take it up to D2L when we're done, and then you can come back and review this if you want to see how we worked out some of the questions. Now, what you should be seeing on your screen now is a fairly large copy of the practice exam. I'll make it bigger in just a moment. And then down at the bottom, on the right hand bottom of your screen, you should see a little thumbnail that's showing right now my hand. And if you want to make that bigger, all you've got to do is click on that image down there at the bottom, and your screen will go to full screen. And that'll make it easier for you to see. I want to record this way because if I record like this, my image that I record will actually have both things on it big enough to see. One of the things I noticed when I did the recording before was it recorded just like that. So even when I was working on the small screen over here, it might have looked big to you and me, but it didn't record that way. It recorded exactly the way it's showing on here now, with the big one image here, and then that little tiny one for my webcam. So I'm going to record the other way from now on, so that we'll have a good image of everything that we're doing. Okay, so I think we are ready to go. So let me maximize this screen, which will make your screen bigger. And I think I've got it as big as I can make it now on your screen, except I'm going to do one little thing up here. I'm going to change view. I'm going to zoom it. I think I can get to 200, and it'll only maybe show one or two questions on your screen when I do that. But it'll be big enough to read if I get it put over there like that. So that should make it so that you can see everything in there. So right now you should be looking at number 22 on the practice exam, big enough to see what you're doing. Now, I'm going to pull up to the top and just kind of come back down through these. Is there any of you that want me to work? Well, I tell you, let's do it this way. If any of you have a particular problem on the practice test you would like me to work for you, just open your mic and tell me that. And the way it's set up, I think whoever's mic comes open first and says something, that's the one I'll hear. So if any of you got any of these that you want me to work first, tell me now. We'll do that one, and then we'll work out the ones you have questions about. And then I'll come back and just work down the list until we run out of time, okay? All right. Anybody got one you want me to start with? Okay, hearing none, we'll start with number 1. Now, remember, you can easily maximize this place where you see my hand now. Once we look at a question, if you've got them printed out, it'll be okay. I can switch back and forth, and I'll do that, but it'll take a little more time to do it that way. Okay, so the first one is the formic acid is HCOOH. Is the acid, it's Ka, is 1.8 times 10 minus 4. I wrote it EE because I was having some trouble at the time getting the formatting to work on my program. So this is the way you'd enter it in the calculator. 1.8 EE minus 4 would be the way you'd enter this number on your calculator. So we've got a solution is prepared by adding 0.00570 moles of formic acid. So I got, this is 0.00570 moles of the acid to 150 in a 150 milliliter flask, volumetric flask, and diluted to the mark. So we're going to have 150 milliliters of the solution. What is the equilibrium concentration of the formic acid? So here's what we're going to do first. We're going to take the concentration of HCOOH that we started out with, and that's going to be the number of moles, 0.00570, divided by the volume is 150 times 10 to the minus third milliliters. This is moles now per liter. That's molarity. So if I do my calculation.
You said that was 10 to the negative third, correct?
I'm sorry?
You said that was 150 times 10 to the negative third?
Yeah, it's milliliters. See,
Okay.
on your screen, that's the best way. That's a good question, actually. The best way to do the conversion, remember, you have to have moles per liter. So you probably are comfortable with just moving a decimal point back. But every once in a while, people will do that the wrong direction or make a mistake. The way you want to convert within the metric system is just replace that prefix with what it's equal. So it's 150 times 10 to the minus 3. That's what milli is. 150 times 10 to the minus 3 liters. Now I've got moles per liter. That's the right unit. And also I'm going to enter it in my calculator that way. So 0.0057 divided by 150 with an exponent, EE, of minus 3. And that should have been divided. There I had times. Divided by 150 exponent minus 3. Now my screen looks right. And so I'm started out with an initial concentration of this acid. That initial concentration is going to be 0.0380 molar. Now, that's not equilibrium concentration. What's going to happen is the HCOOH, formic acid, is going to dissociate to H plus HCOO minus. This is the hydrogen that comes off, the one that's always attached to the oxygen. Okay, so that's the equilibrium that's going to be set up. We started out with 0.0380 molar this, none of this, and none of this. At equilibrium, we'll have X moles per liter of this and X moles per liter of this, 1 to 1. And we will have this much minus X, 0.0380 minus X for this. So my Ka is going to be equal to this concentration times this one. So X times X is X squared over this concentration, 0.0380 minus X. And that's going to be equal to my Ka. And the Ka in this case is 1.8 times 10 negative 4. Now the way I'm going to solve this, instead of cross multiplying, collecting terms, and then putting it in the form ax squared plus bx plus c equals 0 and using the quadratic formula, that takes too long. So what I'm going to do is I'm going to say x squared is going to be equal to 0.0380 minus x times Ka, 1.8 times 10 minus 4. So my x is going to be plus the square root of, we can't have a negative value here because I know it went to the right. So it's 0.0 0.0380 minus x times 1.8 times 10 negative 4. Okay, now this is set up to do successive approximations, and we're going to see this works pretty fast. What I'm going to do as a first guess is I'm going to, if x were 0 on this side, what would I get for my first approximation over here? So x1 is going to be 0.0380 times 1.8 times 10 negative 4, and I want the plus square root of that. So let's do the math. I've got now notice this, I've got this previous answer still on my screen, 0.038. So all I have to do is say times, and my calculator says answer times 1.8 with an exponent of minus 4. I get this number. And then I take the square root. Second square root, second answer is. So this first approximation is 0.00265 and a bunch of other digits. So now what I'm going to do is take this answer and put it back in up here and do it all over again. My second approximation then is going to be the square root of 0.0380 minus my answer. That's still on my screen, that number there, times 1.8 times 10 negative 4, and I need to take the square root of that. So I still got it on my screen, so here I go. 0.038 minus my answer equals times 1.8 with an exponent of minus 4 equal second square root, second answer equals. And now my next approximation, this one is 0.0025, 2, 3, some other digits. And up here the last time I had 0.0261. So I have not completely had the second significant figure stabilize. So I want to take that answer, put it back in here again.
Dr. Pierce,
Yes.
right here, you lost me at the x sub 1 equals the square root of.
Yes. The first thing I did, these are always going to look like this. It's going to be the square root of C0 minus x times Ka. This is going to be a common setup for every one of these kinds of problems. So all I need to do is the initial concentration. I need the Ka. So for the very first step, this one here you're asking about, what I put in for x was 0.
Yeah, I got that part.
I didn't include it. So I just took C0 times Ka and took the square root. And when I did that, can't read it on there, it's 0.0026153394. So 0.0026 is the thing to look at. The one I just did when I took the answer I got previously and put it in for x. So once I get an answer, instead of putting a 0, I'm going to put that answer in here. And then I'm going to subtract and multiply by Ka and take the square root. And I'm going to do that over and over again until I get the correct answer. And I'll know when I got the correct answer when in the third significant figure, I only needed 2, but when the third one stabilizes to the same number, I'm done. So now if I take this answer, and that's what I'm going to do again, I'm going to take 0.038 minus that answer, 0.038 minus the answer I just calculated. And that gives me, this part here is 0.0354. I'm going to multiply that times 1.8 with an exponent that's -4. And then I'm going to take equal. Now I've got all of this under the radical sign calculated. It's 6.3857 times 10 - 6. Now I'm going to take the square root of that. Second square root, second answer is. Flip. Let's see, what did I do wrong? Okay, I can see what I did wrong. Okay, I pushed the wrong button. Okay, second answer minus. No, I do not want to do that. I want to just back up. Okay, get back on my calculator. And I want to delete all of this. And I want to take, okay, I've got my right number back in there. Now I want to take the square root of it. Second square root of the second answer. All right. Probably been easier just to start over. Okay, now I got it finally. This one comes out to be 0.00257. You know, I think that's going to be close enough. 252, 257. I think this would be 253, not 7. It's 3. So this one and this one are almost the same. It's the plus or minus 1 in the third significant figure, but I only need 2. So I think I'm going to stop right here. I'm going to say the hydrogen ion concentration, that's the X I just calculated, is going to be 0.00253 molar. Now, what did the problem ask me to do? Oh, now this is the hydrogen ion concentration. So I'm looking, that's not the right answer. I'm glad I didn't put it up there. I would have been suckered in. The answer I want is 0.038 minus X for the HCOOH concentration. So the HCOOH concentration is equal to 0.038 minus 0.00253. So let's do that. So 0.038 minus that answer gives me 0.0355. Yes, that's right. Is 0.0355, and that's C on the exam. Okay. All right. And so that's how we do number 1. Okay. Now let's see about number 2, unless you have one you want me to do next. Okay. Now this is going to be kind of nice. Looking at the form of this, I'm using the same acid with the same constant and the same amount dissolved. So I want the pH of the solution. So really, I've got the answer already for the hydrogen ion concentration. We just did that a moment ago. If I could find what I did with it. Well, we got okay, yeah. So the hydrogen ion concentration that we calculated from the first one, the hydrogen ion concentration was 0.00233. So this one was the pH. pH is equal to negative log of the hydrogen ion concentration. So it's negative the log of 0.00233. No, 253. I can't read my own writing. 253. Okay? Now, be really, really careful. And I wish every one of you would just do this with me on your calculator. Here's what I'm going to do. In most cases, this number might still be on your screen. So I'm going to put it in there so that it is on mine. 0.00253 equals. And now that number is saved on my screen, and it's saved internally in the calculator as answer. So what I'm going to do now is take the negative logarithm. Do not use that minus sign on the side of your calculator. You're looking for a key that's got a negative sign inside parentheses. So that tells it to change the sign of. So I want to change the sign of the log, and that's the key I need to use. Minus log, second answer, close my parenthesis, equals. Now, if you do that correctly, you should get 2.5968 and a whole bunch of other digits. Now we want to do round off, and I want to show you something. This number right here is 2.53 times 10 to the negative 3. Now this has got 3 significant figures in it. Actually, we only need 2 because our Ka was 1.8 times 10 to the negative 4. I think it was from up there. Yeah. So this only has 2 significant figures. This is going to have one more than it needs, but I'll just go ahead and illustrate the point. Now, if I'm taking the log of this, what do you do when you have a product? You take the log of this number, the log of 2.53, and you add the log of 10 to the minus 3. Now, this part right here, log of 10 to the minus 3, is just going to be minus 3. And so what you're going to, yes. So whenever you take the log of a number like this, you take the log of this is going to be point something or other, and you're going to subtract 3 from it. And what you're going to come up with is minus 2 point something or other. And then out here, we're going to change the sign to a plus. And the point is, this digit right here, this 2 that we got right there, is not a significant figure. It came from the exponent part of the problem. So whenever you're talking about significant figures, if I wanted 2 significant figures here for the pH, which is what I want for my answer, I would write 2.60 as my pH. And so that should be what is recorded for the answer, and it is ND. But that's only 2 significant figures when you're talking about a pH. This digit came from the exponent, and the exponent does not include any significant figures. The significant figures of a number like this is in the mantissa part of the number. Now, the way I wrote it here, I should have had another decimal place on the pH, but that would have been wrong because I only used 2 significant figures in Ka. All right? So that's something that you need to keep in mind. If you take quant next, Dr. Lee will trick you on that. Count on it. All right. All right, number 3, unless someone has a question about something else. Consider the hydrogen sulfate ion, identify the conjugate acid, conjugate base of hydrogen sulfate ion. So the first thing you have to know is what in the world is hydrogen sulfate ion? Hydrogen sulfate, sulfate's -2, hydrogen +1, that's a -1. So that's what hydrogen sulfate is. What is the conjugate acid and the conjugate base? The conjugate acid is what you get when you add a hydrogen ion.
Can you move your paper up a little?
Yeah, oh yes, I'm sorry.
Thank you.
There we go. Thank you for reminding me. Sometimes I'm looking on the little tiny postage stamp size, so sometimes I don't see what you're seeing. Okay. The conjugate acid is going to be what you get when you add an H plus to this. Adding an H plus to this is going to give me H2SO4 is the conjugate acid. Now, if I'm taking a test, I'm going to look and eliminate answer A and D right now, because that's only B and C have the correct conjugate acid. Conjugate base is going to be what you get when you take a proton away. So if I take a proton away from HSO4 minus, I get SO4, 2 minus is the conjugate base. And that's going to be answer C. Okay? All right. And moving right along. Nope. Number 4, unless you have something else you want me to do. Okay. Number 4. We're given the Ka of HCNO, and we're given the Ka of HF, and the Ka of HNO2. So you can watch those over there, so I'm not going to copy all the numbers down over here. I'm just going to start working on the problem. Number 1 is HCNO plus F minus goes to HF plus CNO minus. And of course, this reaction can go both ways. And the question is, which of these reactions go more than 50% to the right? So what I'm going to do, this is the acid going to the right. This is the acid going to the left. So I want to see which of these two are stronger. HCNO, the Ka is 3.5 times 10 to -4. The HF is the second one, 6.3 times 10 -4. So if I'm comparing these two, 6.3 times 10 -4 is bigger than 3.5 times 10 to the 4. So this is the stronger of the two acids. That will push the equilibrium more than 50% this direction. Okay, so number 1 is not the correct answer. So number 1 can't go more than 50% of the right. So A and D are out right now. Now, number 2, let's see about reaction number 2. Number 2 is HNO2 and CNO minus, and we're going to HCNO and NO2. Now, the acid going to the right is this one. Acid going to the left is this one. So I want to compare HNO2. HNO2's Ka is 5.6 times 10 -4. And HCNO is 3.5 times 10 negative 4. So this one is stronger. And it does go to the right, greater than 50%. So only number 2 goes to the right more than 50%. That's answer C. So we're done. Are we good so far, everybody? Okay. All right, what did we do? Okay, I'm ready for number 5. I want to jump, do a page jump right there. It's kind of hard for me to get everything on the screen. There we go. Consider nitrous acid is Ka, and Kb for ammonia is this. Consider aqueous solutions of the following salt, which will be acidic. Okay, I'm going to go down here and eliminate some that I know. Let's look at this first salt. It's sodium nitrate. So number 1, it's NaNO3. Now, how would you make that? You would make that from NaOH plus HNO3. That's how you would make that. This is a strong base, and this is a strong acid. So this salt is neutral. So it's not acidic. So what I'm going to do right now is if I see an answer that has it in it, I can eliminate it. Well, that's only C is the only one I can eliminate. Now let's look at salt number 2. Salt number 2 is NaNO3. No, I just, NO2, sorry, read it wrong. Okay, how would you make that? Well, you would make that from NaOH plus HNO2. Now, this is a strong acid, a strong base rather, and this is a weak acid. So the strong base will dominate. This is going to be a basic component. And what does it say? Which will be acidic? Well, it can't be anything that's got 2 in it. All right, so that eliminates number B and C in this case.
Will you move your paper down once more?
Down, up.
Or up, yes.
Yeah, okay.
Thank you.
All right. Thank you. All right, so neither one of these two are correct. They're neither one, this is neutral and this one's basic. What about number 3? Now let's go to number 3 first, because that'll be the easiest one. Number 3 is going to be ammonium nitrate. Yeah, right, nitrate, yeah. No, it's NH4, nitrate, NO3. Now, again, how would you make this one? Well, you'd make it from NH3 and HNO3. This is a strong acid. This is a weak base. So the strong acid dominates. This solution is acidic. Okay, so this is a possible answer. I'll put a question mark by it. It could be, but I don't know that. Let's see. Number 3 is in 3 of the answers, so it wouldn't help me at, well, it's in all 4, isn't it? Okay. All right, so let's get to number 4. Yeah, I haven't eliminated 1 yet. So in number 4 is NH4NO3. Now, NO2, nitrite, yes, NO2. Now, both of these can hydrolyze, but how would you make it? Well, you'd make this from NH3 and HNO2. This is a weak base and this is a weak acid. So which one is stronger? Well, the Kb for the base is 1.8 times 10 negative fifth. The Ka for the acid is 5.6 times 10 negative 4. So this is stronger. So this salt is going to be acidic. And so number 2 and number 4, number 2 and number 3, 2 and 4 rather, 3 and 4 are correct. They both are. So this one and this one is shown in D. Answer D. Okay. So correct answer to that one is that both 3 and 4 are done. So you can see how you should make your comparisons. Look at the ones and see how you make them. Each salt is going to have an acidity based on which of the two, the acid or the base, was stronger when it made it. And this one, sodium nitrate, doesn't hydrolyze at all. It's a strong base, strong acid, so it's neutral. I can eliminate everything that had number 1 in it. So that did definitely get rid of that guy. And then when I did sodium nitrite, the anion is the one that's hydrolyzing. It's going to be basic. So number 2 is certainly not acidic. So everything that's got 2 in it is out. So I can eliminate B as well. Then I looked at the other one. This one, ammonium nitrate, it's the acid that hydrolyzes. So sure enough, 3 is one of the answers. It could be now either 1 or A or D. But then when I did the ammonium nitrate, it eliminated, it added D, number 4, also as a possible weak base. Okay. I'm sitting here just broke my arm patting myself on the back for that question. That was a good question. This is so tiny, it's making it hard for me to. Well, I'll try it, but we're going to go across a page, a silly thing. We were trying to find number 6, aren't we? Okay. Solution prepared that many moles of fluoride. What's the pH of this solution? So now this one is just exactly like the earlier one we did, I think. Maybe different concentration. We've got HF, and it dissociates to H plus F minus. This is number 6. C0, 0, 0, X, and X, C0 minus X, and Ka is equal to X squared over C0 minus X. X is equal plus square root of C0 minus X times Ka. So essentially, we're setting that equation down. What I need is Ka, which I do have, and C0. Initial concentration is 0.057 moles in 150 times 10 minus 3 liters. That's C0. I'll divide it out. 0.057 divided by 150 exponent minus 3 is that. Second square root. Second answer is got too big. Forgot to turn my calculator on. Let's do it again. 0.057 divided by 150 second exponent minus 3. All right. So it starts out at 0.380. So my first approximation to the answer is going to be the square root of 0.038 minus X times my Ka is 6.3 times 10 negative 4. Okay, now let's do the math and get the first approximation. Oh boy, I almost did it. Skip all that. I didn't read the problem all the way through. I thought, hey, this looks just like the other one. We had calcium fluoride. And that's the formula for calcium fluoride. So it's going to completely dissolve. It's a chloride, fluoride, or bromide, or iodide that are soluble. It's going to give me calcium plus 2 and 2 F minus ions. Now the fluoride ion is what's going to do the hydrolysis. Fluoride is going to react with water to set up an equilibrium of HF and OH minus. Now, it's going to still be the sort of the same thing. I'm going to have some initial concentration, and now my initial concentration, though, is not, I guess it is. It's 0.057 moles of calcium fluoride. Okay, so I'm going to have 0.057 moles. And when this completely dissolves, I'm going to get 2 times 0.057 moles of that. And so this concentration is 2 times 0.057 divided by 150 times 10 minus 3. So now let's do that math. Got that is on the screen, times 2 is this. And so it looks like I'm getting my initial concentration for fluoride ion is 0.76 molar. So my x squared divided by 0.76 minus x is going to be the constant for this is the Kb for this ion, which is Kw, 1 times 10 minus 14, divided by the Ka for the acid is 6.3 times 10 negative 4. So my x is going to be plus square root of 0.76 minus x times 6.3 times 10 negative 4. No, that is divided by 6. It's 1 times 10 minus 14 divided by 6.3 times 10 negative 4. And again, we're going to do the same thing we did before, put 0 in there. And if I do that, I got 0.76 on my screen times 1 with an exponent of negative 14 divided by 6.3 with an exponent that's negative 4. I get that number. Well, I didn't. Clear. Do it again. 0.76 times 1 with an exponent of negative 14 divided by 6.3 with an exponent of negative 4. And then that's like 1.21 times 10 negative 11, second square root, second answer is. And now come up with x is going to be 3.47 times 10 to the negative 6. Now here's a case where I'm not going to do another approximation because you see, this is 10 to the negative 2. I'm subtracting something 10 to the negative 6. It's not going to matter. I'm going to get the same answer again. Now this is going to be the OH minus concentration. So I'm going to do POH. and that's going to be minus log of my answer that's on my screen, 3.47 times 10 minus 6. And so I take minus log second answer is 5.46. My guess is that's probably one, well, it's not, but I would have expected it to be. Maybe I've made a little math mistake up here, I don't know. And pH is equal to 14 minus the pOH. Okay, so 14 minus second answer is 8.54. And that's answer A. Okay. All right. Moving right along. Ready for number 7. Which of the 4 acids listed below is expected to be the strongest acid? Well, let's look at them. All of them are weak acids. So essentially what this is really an exercise in nomenclature. If you don't know what the formula of these things are from the name, you're kind of sunk. Hypobromous acid. It comes from hypobromite. Hypochlorite is on your list of OCl minus. That's hypochlorite. So hypobromite is OBr minus. And so hypobromous acid is H. I'm going to do OBr. That's the way it's actually bonded. And chlorous acid comes from ITE-ion. So chlorite ion, I memorized, is ClO2 minus. The acid is HOCl. That's chlorous. HOClO. Yeah. HOClO. HClO2. I wanted to put it written like this for a point that we'll make in a moment. And then hypochlorous acid is going to be from here, so it's going to be HOCl. So this one was A, this is B, this is C. And bromous acid is from bromite on, so it's going to be like that one, HOBRO. Okay, now, let's look at all of these acids. Now, if I'm looking at these, there are 2 types. There's this one and this one. This is D. And there's this one and this one are similar. Now, the only difference between these 2 is a chlorine in the acid or a bromine. The more electronegative is the stronger acid. So I can eliminate that one right now from the answer. Now, let's compare these 2. Okay, again, I've got oxyacids. They both have the same number of oxygens, but this one has bromine, this one has chlorine. So this one is not as strong as that one. So this one I can also eliminate. So it's got to be between these 2. Now these are oxyacids and they both have chlorine. This one has 2 oxygens attached. This one has only 1. So this one is going to be the stronger one of the 2. Oh, yeah, that's right, HClO2. That's right. Right. Now, the reason why I wrote them like this is so you could see the bonding in every one of these cases for the acidic proton is through an oxygen atom. So it does not matter at all about the bond strength. Bond strength of that HO bond is the same in all of them. The only difference is electronegativity. And so electronegativity is bigger for chlorine than it is for bromine. So the chlorine acids are both going to be stronger than either of the bromine acids. The one with the most oxygens is going to be the bigger one of the two, because adding more oxygen adds more electronegativity to this side, pulls the electrons closer to that ion. That's what makes it work. Oh, we're already over. So I know some of you, maybe most of you, have to leave now. I'm not sure whether I'll have time to complete the recording for the rest of the practice quiz or practice exam. I will make an effort, and if I can get through it all with a recording that doesn't take up all my memory, then I will record it and post it. So any of you that need to leave now, you're way overdue already. So I'll continue for those of you who can stay, and I'll continue to record, and I'll post this on D2L if I may, whatever I'm able to get recorded. Okay. All right. We look at the Arrhenius acids, Bronsted-Lowry, and Lewis acid bases. Which of the four identifies a Lewis base? So if we're talking about Lewis base, now Lewis has to do with electron pairs. Now, what I like to do is, like I told you a while ago, you don't want to memorize both of two alternatives. So what I remember is the Lewis base is, let's think of an example. Here's ammonia. And we write the Lewis structure for ammonia. That Lewis structure contains a lone pair of electrons. So when this reacts, it's going to be the electron pair donor. So if ammonia attaches itself, for example, let's take a silver ion, Ag+. It will react with two ammonias and it will make NH, H, H, Ag, N, H, H, H plus. It will make that diamine silver complex. So when it forms this product, the ammonia donates its pair of electrons to the silver to create that bond. The pair of electrons that was on ammonia attaches itself to the silver on this side, and the pair of electrons that was on ammonia on this side attaches itself. It makes a linear nitrogen, silver, nitrogen type of structure, and it would, the ammonia is the electron pair donor. So this is the electron pair donor. That's the correct answer to this one. Proton donor, a proton acceptor. A proton donor would be a Bronsted-Lowry acid, and a proton acceptor would be the Lewis base. And there's the alternate to that one as well. Okay. Okay, formic acid. Calculate the pH of the solution that's 0.15 molar in formic acid and 0.55 molar in ammonium formate. That's going to be a buffer. And the pH of a buffer is equal to the pKa plus the log of the anion concentration over the acid concentration. Now, so I want minus log of Ka 1.8 times 10 negative 4 plus the log, and the formic acid concentration, that's on the bottom, it's 0.15. The sodium, aluminum formate, watch out. Okay. AlOH, OC, yeah. I'm going to take off HCOOH, HCOO minus, and aluminum's plus C, there's going to be 3 of them. When we have the aluminum dissolve, we're going to get 1 aluminum plus 3, but we're going to get 3 HCOO minus for each one of these. So if the solution is 0.55 molar in ammonium formate, the formate ion concentration is going to be 3 times that much. So it's going to be 3 times 0 times 0.55. And I'll just go ahead and put that in right there. 3 times 0.55. Okay, now I'm going to do the math. Okay, so I want minus log of 1.8 with an exponent of minus 4. Close that parenthesis. Be sure to do that. And I want to do plus the log. My left parenthesis, my calculator puts that in. So I'm going to do 3 times 0.55 divided by 0.15 and close my parenthesis. So my screen is reading minus log of 1.8 times 10 to the negative 4 plus the log of 3 times 0.55 divided by 0.15, and I've closed the parenthesis around that. So that should be correct. So I'm getting 4.79, 4.786, whatever. There it is. It is answer C on the test. Okay, I'm ready to do number 10. Calculate the pH of a solution. It's 3.2 times 10 to the negative 3 in formic acid, and 1.5 times 10 to the negative 2 in formate ion. Well, that should be even easier. It's just pH is equal to pKa is minus log of 1.8 times 10 negative 4 plus the log. Now the formate ion concentration is given directly, so I don't have to do any bad stuff to this. Formic acid is 3.2, that's the denominator, 3.2 times 10 to the minus 3. My numerator is 1.5 times 10 negative 2. So all we got to do now is do that math. So I get minus the log of 1.8, exponent is negative 4, close the parenthesis. No, it's plus the log of 1.5 with an exponent that is minus 2, yes, divided by 3.2 with an exponent that is minus 3, close my parenthesis. I'm checking my screen, minus log 1.8 times 10 negative 4 plus the log 1.5 times 10 negative 2 divided by 3.2, 10 negative 3, close the parenthesis, that looks right. So I should get 4.38. That's what I get. Oopsie daisy. $1.5. Did I do that? Did I set that up right? I have 1.5 times 10 negative 2 in formate ion, that's right. And formic acid is 3.2 times 10 negative 3. And the Ka is 1.8 times 10 negative 4. Well, let me run the numbers again. I'm not getting the answer that's on the test. Minus log of 1.8 with an exponent of minus 4, close the parenthesis, plus the log of, my parentheses opened already, 1.5 with an exponent of minus 2, divided by 3.2 with an exponent of minus 3, close the parenthesis. Minus log 1.8 times 10 plus the log 1.5, 10 minus 2 divided by 3.2, 10 negative 3. Okay, I did push a button wrong a while ago. It's 4.42. Yeah, okay. I thought I proofread this thing enough that I didn't have mistakes on the practice test anymore. Okay, now let's go to the next one. And probably I'm going to have to leave after this one. I've got an appointment that I've got to keep in 30 minutes across town a little ways. Okay. What mass of formic acid is contained in 250 milliliters of a buffer containing 50 grams of sodium formate? Now, this is kind of a tough problem, so I think I'll just start with a fresh piece of paper, just to be sure we get all of this without confusion. Okay, now, I see my recording is going to be messed up already. I forgot to do the screen share after each one. Okay, well, here we go. What mass of formic acid is contained in 250 milliliters of buffer containing 50 grams of that if the pH of the buffer is 4.24? So pH equals pKa plus the log. Now, here's what I'm going to do. I need to solve for something in here, so I'm just going to call it the ratio. And R is going to be formate ion concentration over acid, formic acid concentrations. So now the pH that I'm going to get is 4.24, is minus the log over here. So I'm going to bring the log over here just to save us some time. Plus the log of the Ka is equal to the log of R. Okay, so there we go. So I'm going to write 4.24 plus the log of 1.8 second exponent minus 4. Is that correct? Yes. Close it. And what I've got over here, this now evaluates to 0.495 is equal to the log of R. So if I raise both of these to the 10, raise 10 to each of these powers, then the right-hand side just becomes R. So second 10 to the second answer. This number, 10 to that power, evaluates to 3.128 and some other digits. Now, let's plug that in to our ratio and what we asked to find out. We're asked to find out what mass of formic acid. So I'm going to get the the concentration of the formic acid. That I don't know, but I must know the amount of the buffer in sodium formate. So my sodium formate that's the sodium formate formula. Sodium formate is going to release one formate ion for each amount of that. So let's see how many moles of that stuff we have. We had 50 grams of sodium formate. And since I didn't want to give away nomenclature, I didn't tell you what the formula was, so you have to figure it out. So it's going to have one sodium, that's 23. It's going to have one hydrogen, that's 1.008. It's going to have one carbon, that's 12.01. And it's going to have two oxygens, that's 2 times 16. So let's do the math. 23 plus 1.008 plus 12.01 plus 2 times 16. 23 plus 1 plus 12 plus 2 times 16. I'm calculating this mass to be 68.02 for the AMU of that. So I've got 50 grams divided by 68.02. That's moles. And I want to put it per liter. It's in 250 milliliters. Okay, so here we go. We got 50 divided by the molecular weight that I still have is that, and divide that by 250 with an exponent of -3. So I'm coming out here, this comes out to be 2.94 and digits molar. So I'm going to put in 2.94 molar here. And now I've got this. Okay, so my HCOOH concentration cross multiply is going to be this number divided by this one. So that's going to be 2.94 divided by 3.128. So this number is still on my screen, so I'm going to divide that by 3.128, and I get this to be equal to 0.94 moles per liter. Yeah. Okay. That's in moles per liter, yeah. 2.94. Okay. Now, and I have, what does it ask me for? It wants to know what mass of formic acid. Okay, it went all the way to the hard way. Okay, so I've got that many moles per liter. I want to multiply that by 0.250 liters, 250 milliliters. So I'll multiply that by times 0.25. Yes, it was 250. And I get 0.0235 moles of the formic acid. And now I want to multiply by the molecular weight. And yeah, I know I'm going to be there in just a minute, huh? Okay, so I'm going to now multiply by the molecular weight, and essentially formic acid is HC, so it's 2 hydrogens, so it'll be times 2 here. It's 1 carbon and 2 oxygen. So if I just do this part here, I'll get the molecular weight for the formic acid. So it's 2 times 1.008 plus 12.01 plus 2 times 16 is 46.026 AMU. Now let's go back. So it is 46.02 grams in 1 mole. So if I take the 0.0235 times 0.0235, I should get 1.08 grams. And I hope that's the right answer. Oh, I missed a factor of 10 in there somewhere. Oh, yeah, I've multiplied. That's supposed to be 0.238. And so that is 10.8 grams, which is correct. And that's A. All right. So I'm going to close out the session now. And this is as far as I'll be able to get with the recording. So I want to stop the screen share and I want to end the meeting. All righty.